Swayam Prabha. Digital India. Educated India.
So far in this course, we have discussed calculus of variations, its history and the kind of problems that you encounter in geometry and mechanics. And then we took detour for 3 lectures where we learnt about the theory of finite variable optimization, right, both necessary and sufficient conditions. So, we really are now waiting to go to calculus of variations, but before that there are some formalities I must say, or what we call mathematical preliminaries. Okay. So, we need to discuss these mathematical parts, preliminary part of it before we jump into calculus of variations. In this the one thing that we need to understand is the notion of what is called a functional. Normally in finite variable optimization that we have already discussed, the function is what will be there as objective function, that is why we call it objective function or constraint functions. Whereas in calculus of variations we have what are called functionals. We have seen that in the lectures that discussed the kind of problems we encounter in geometry as well as in mechanics, which are cast in the form of calculus of variations, where the unknown is a function itself. In a finite variable optimization, we have unknowns as finite variables. They are continuous like x1, x2, x3, they are continuous over a domain, but they are finite in number, right. In calculus of variations, we will have function itself as an unknown, such as if I just take the Brachistochrone problem that we say there is a point here, there is a point here and there is gravity acting. We say to go from point A to point B, we want to find the function that passes through these points and takes the minimum time. That is what, if you remember, is what is called the Brachistochrone problem. Okay. So, this function, if I call it y of x, that is what we do not know. We want to find that one which minimizes the time. So, if I say x here and y of x here, so we will get some functions, there are a lot of them. Let us say point A is here, point B is here, there are a lot of functions that are possible. We want to know which one of them will be the answer, that is the one that minimizes the time. Now, the time that we had, if you recall, we had like an integral, right. So, this time of descent, if I keep a little bead here for it to fall and come over here, there is certain time taken. That time turned out to be integral, where if I say this is x here, right. So, the 0 to let us say h, it was 0 to h, and we had something which dependent on this y of x as well as dy by dx. That is what we had. Okay. So, here this is called a functional. So, in calculus of variations, we minimize or maximize what we call a functional as opposed to minimizing or maximizing a function in finite variable optimization. So, there the variable were x1, x2, x3, xn, whereas here we will have y of x. We can have more than one also, we can have y1 of x, y2 of x and many functions as unknowns, but the fact is that the function is the unknown and what we minimize is actually called a functional. Okay. If you look at that, the integrand of the functional, when the function is the form of an integral, it need not be of the integral form. A functional is more general than being an integral. When it is in integral form, such as the one that happens for this Brachistochrone problem, then the integrand depends on the function and its first derivative. Again it can be any number of derivative, not be only one derivative, it can be just the function and the first derivative, second derivative and so forth. Okay. So, such a thing is called functional. Understanding functional in this manner will only take us that far. We need to know a proper definition of what a functional is, okay? Because when we understand the functional and then how that functional depends on the functions. So, here y of x is our function, right, and its derivatives also are there. So, among all these functions that exist, so let us say I want to find a particular function, let us call that y star of x. So, here let us say minimizing time is obtained by a particular function which we know as a cycloid. Okay. Let us say cycloid is given denoted by this y star of x. We need to find it by searching through a number of functions. So, we do not know, there are a lot of different curves that are possible that go through these, right. So, among all of those functions, let us think of a set of all these functions. Let us say there is a y1, there is a y2 and there is a y3 and so forth, many functions, but there is also lurking there y star which is our answer. Okay. We have to search in this space, okay, which we actually call a function space, just like our variable x belongs to a real number space. Okay, x1, x2, x3 each of them belong to real number space. Similarly, here we have to deal with what is called a function space, a space that has a lot of functions. Now, which function, what kind of function, what are its properties, that is something that we want to discuss today, which is what we call mathematical preliminaries of calculus of variations. The first one you want to understand is a functional. Okay. Before we discuss what a functional is, we can actually talk about or remind ourselves what a function is. Okay. We want to talk about functional, but let us talk about what functional is our aim, but let us first see what a function is first. There is a lot of text here that you can read leisurely. Let us just discuss. This text is written so you can understand offline as well, but let us jump in and then see what a function is. Okay. Okay. A function which is highlighted here, if you read, it says a rule which assigns a unique real, or in brackets we have put complex. Let us leave out that parenthetical part now. A rule which assigns a unique real number to every x belonging to omega, some domain over which this function is defined, is said to define a real function. So, that means that for every x there is a unique f of x or y of x, whichever symbol you are using to denote the function. That is what a function. Function is a rule. It says that in the domain, let us say x1 to x2 is our domain. In that real line, if I pick any point, I would like to know a unique number that is that function. Okay. That is, if you have if you draw, let us switch here. Okay. So, let us say I take x axis, okay, this is our x axis. I define my domain, let us say somewhere x1 and x2. Okay. Let us say there is an origin here. All right. Now, I want to define a function y of x or f of x, whichever. Now, any value I take in the domain x1, x2, there must be a unique value y of x. If I take another point, another one. If I take another point, there should be another one. So, if I do that, I should have a function, something like that. So, for any value that I take over here, there should be a unique value for y of x. That is what is a function, right. We all know intuitively what a function is. Let us understand what a functional is in the same intuitive way. Okay. So, we understand what a function is now. The domain of the function depends belongs to a real number space, what is shown as Rn over here, okay, or complex number if you take Cn, where n depends on dimension. Let us say you have a function that depends on x1 and x2, then domain of that function is a 2-dimensional space, because you have to identify 2 real numbers to calculate that function. Similarly, you can have in 3D x1, x2, x3, that will denote as R3. If it is a complex number, it will be C1, C2, C3 and so forth. Okay. And the domain has to be non-empty, open set. Those are all the mathematical rigor with which people define, because if you do not have a domain, then you cannot define a function. That is why it should be non-empty, and it should be open set, meaning that it will lack the boundary. There are also reasons why people define it in that manner. Okay. This open set, right, that we need to understand. So, why do we need this open set or open ball? From the optimization viewpoint, if you think, so far whenever you defined what is a minimum, we always talked about that minimum characterized as a local minimum, that is only in the vicinity of that point it is a minimum, or if you say something is local maximum, in the vicinity it is a maximum, not everywhere, not like a global minimum or a global maximum, right. So, in order to have that vicinity around every point, you should have like an open ball, that is you should be able to define a point, a set of points around that point. In 3 dimension it will be like a ball, in 2 dimension it will be a disk, 1 dimension will be small segment. Around a point there will be plus and minus side, neither side you will have a few points. Okay. So, the open set is something that is defined here, a set S let us say belongs to real or complex domain. At every point of S, there is center of an open ball, that is at every point there is an open ball, then that is like a point that will have open in the sense it does not contain the boundary. If something on the boundary, on the other side there is nothing. If it is inside, there are points all around, that is what we mean by this open set. So, that at every point there is open ball, so that we can check whether a point is local minimum or maximum. So, whenever we want to check, around that point there should be a few points. If it is not there, we will have trouble, right. So, that is why this concept of open set is important for a function, and so is it is for the functional as well. Now, we come to the definition of a functional. So, a functional is a particular case of an operator in which R A, which is the range of that domain that you have, belongs to real or complex number. Let us not worry about complex numbers now, just focus on real numbers. What it says is that a functional is simply an operator that assigns a real value for every function that is there. So, if we go back to our notion of a space, okay, let us call this for now a function space which contains all functions. There will be y1, there will be y2, there will be y3 and so forth, let us say yn and so forth, and then there will be some y star also that we are after. We want to find that minimizing function. So, what this functional does is, we have the real number space, okay, let us say this is R1 or just R, that it contains all real numbers. I could have drawn it like a line also, okay, real number space, I can also put a real line, right. What this functional does is, it takes every function, let us say I take this y1, it is a point in the function space, there will be a corresponding point in the real number space, okay. That is what a functional does. Function is the operator that takes a function, okay. Let us say y3 will have a point and y star will have a point and yn will have a point and y2 will have a point and so forth, okay. For every one of them there is a corresponding real number, that is what is a functional, okay. Just like a function is a mapping, or what we said, there is a correspondence from real number, that is real number here, to a point that corresponds to this y here, okay. In a similar way, a functional takes a function and finds a corresponding real number. Okay, that is what is a functional is. But then we put an operator, so we have to define what this operator. In the definition we said a functional is a particular case of an operator in which the range is real number space. Now what is an operator? Operator again is a correspondence, okay, a of x equal to y. If x is given, it will find y by doing an operation called a of x, like f of x. Okay. So this operator is defined from one metric space to another metric space. We have underlined this metric space, we will define it. What is a metric space? Okay. And there will be the domain and range that you are familiar for a function. So similarly here also, when you say it is an operator, there will be a domain for the operator. You take an element from that, from the domain, and find something in the range, which is the output. Okay. Now we said a metric space, so we have to now talk about what a metric space is. So this is something that you find in rigorous mathematics. You have to define everything precisely. So a lot of definitions will come, and if you really want to know the mathematics of this very well, you should take a course on real analysis or function analysis. That will be a lot of work for engineering students. So what we are going to do in this lecture and the next lectures is to provide you the background to study that if you wish to. Okay. So intuitive understanding of various terms. So let us understand what a metric space is. So a metric space, which is highlighted in yellow here, is a pair x and d consisting of a set x together with a metric d. Okay, that is called a metric space. When you say metric space, that has a metric meaning a measure. What does it measure? It actually measures the distance between 2 points. With real numbers, when you take 2 points, you know how much the distance between them is. Let us say I take a point here, another point over there, distance between them is as long as this pen is. If I take a 2-dimensional thing, if I put 2 points on a plane, I can talk about distance between them. But then we are talking about the Euclidean spaces that we are familiar with, but these spaces can be very general and abstract also. So, a metric space is one where for every point in that space, okay, x belongs to the points or element of that space, there is a distance metric defined. Okay. And this metric has to satisfy 4 properties which are listed here. First of all, this distance has to be non-negative. Distance between 2 points cannot be negative. It can be 0, okay, but it cannot be negative. So, it is non-negative. And second property says that if the distance is 0, that means that 2 elements or points that you have taken must be one and the same. That is what is second property, that is called the 0 metric. Where the metric is 0 between 2 points x and y, then x should be equal to y. And then there is symmetry also, the third property, dxy is equal to dyx. Distance from a to b is same as distance from b to a. If that is satisfied, that is another rule that metric space will satisfy. And the fourth one, which is somewhat non-trivial but yet very obvious, that distance, that metric between 2 points x y is less than or equal to, if you take another point z, distance from x to z and distance from z to y or y to z because of symmetry. Okay. This is called the triangular inequality. It is quite obvious because if I are given let us say 3 points a, b, c, okay. Let us say we take point A, point B and point C. So, this is A, B and C. Okay. We are talking about 2 points, let us say between A and C. What it says that if I take a third point, the distance from A to B plus distance from B to C, that will be greater than distance from A to C. That is very obvious, right. But that is what is a property that this metric has to satisfy. Basically it says that this distance is less than sum of these two distances. That is very obvious, this triangular inequality. Okay. My high school teacher used to call this donkey's theorem, because if you put some grass over here, let us choose some green for grass. If there is grass here and you have a donkey here, that is my rendering of a donkey. Okay. if you ask the donkey to go and take the grass, the donkey is not going to go this way, it is going to go straight like this, right. So, this is a very intuitive obvious thing, but the definition is a definition. The 4 properties for a metric space, we have to understand them intuitively as well as mathematically. Okay. If you define a particular metric, a distance between 2 points that satisfy these properties, then that will be a metric space. Okay. There are some examples given. So, if you see at the bottom of this slide, distance between 2 points can be absolute value. If you take x and y, difference in them take absolute value, that can be a metric, or it could be just 1 or 0. If x and y are different, you say distance is 1, if x, y are the same, you say distance 0, that is also a metric. You can go back and verify if the 4 properties are satisfied, they are indeed satisfied for this, then that is a metric. Or you can have normal distance metric between 2 points, square root of x1 minus y1 square plus x2 minus y2 square if you are given 2 points xy. Okay. Or you can have absolute value of x1 x2 difference, absolute value of y1 y2 difference, add them up, that will be a metric. So, one can define a lot of different metrics that satisfy those 4 properties. Okay. So, the function space that we talk about is also a space such as this one, but we want it to be a little bit more general than what we just defined as metric space. So, we go to what is called a vector space. Okay. A vector space is a little bit more elaborate than a metric space. Okay. And this vector space needs what is called a field, which is denoted by the symbol here k, that has its own 4 properties just like metric has. But then before that, let us think about this vector space. Vector space is a non-empty set x of elements of any kind, they are called vectors. These vectors are not our normal vector calculus or mechanics vectors, that is v1, v2 we say, not that kind of a vector like a speed, acceleration, they are all vectors, right. It is more than that. Okay. The elements of any kind, for example, our function space, these functions will also be called vectors. They have to satisfy certain vector, let us understand as a term rather than our usual understanding of vector in mechanics. Okay. So, this vector space consists of lot of elements together with 2 operations. One is vector addition, you should be able to add 2 things, and scalar multiplication. The scalar multiplication requires this field k, basically our normal arithmetic operations. Okay. And these addition and scalar multiplication are not our usual notion of addition and scalar multiplication, that is why they are denoted with a circle around it. This plus sign encircled will be vector addition, and the dot which we use for multiplication, you put a circle around it, becomes scalar multiplication between a vector element, that element that belongs to vector space, as well as a real number that belongs to the scalar field. The first property is that if you take 2 vectors, if you add them up in this particular manner, you have to define an operation which is vector addition. If you add those 2 vectors, the resultant should also belong to that space, that is what it says. So, the set that you are considering the vector space should be closed under addition, meaning if you add 2 things, you should get that back. Okay. So, in that sense, if I call vectors of any kind, I said if you say a basket full of tomatoes, does it form a vector space, then you should show somebody convincingly that if you take tomato 1 and tomato 2, if you add them up, you should get another tomato. If you show that, then it is fine, but it is not the only property, you have a lot of other properties, right. If you add, you can define that operation of adding 2 tomatoes if you wish, right. That is, I am just saying it is like an abstract way, but that is what this means, that if you define vectors and an addition, vector addition in your own way, you should show that when you add 2 of them, you should get a vector that belongs to the same space. Similarly, you will have this commutative law, if you say x plus y should be equal to y plus x. Okay. And then there are a few more rules like that. There are associative law, x plus y in brackets and then z is same as x plus y plus z. Okay. And there should be an additive identity, that should be some vector in that space where if you add that you should get back the same, add to another vector you should get back that other vector. That means that this vector is a null vector, that is that is denoted with a theta here. So, that is a fourth property, x plus theta should be equal to theta plus x should be equal to x. Okay. And there should be additive inverse also, a negative quantity. If you have 2, there should be a minus 2. Similarly, if there is a x, there should be x prime such that when you add them up you should get the null vector. Okay. Those 5 things talk about addition and basically addition, right, vector addition, first 5 properties. Next ones talk about scalar multiplication. We have a scalar field k which is for now real numbers, right, and there is usual arithmetic operations of addition and subtraction, multiplication, division and so forth. The 6th property says that if alpha belongs to the scalar field, x belongs to the vector space capital X, then alpha dotted scalar multiplication with x will belong to x again. Okay. If you take a element small x correspond which belongs to the vector space and alpha belongs to scalar field, when you multiply them resultant should belong to the same capital X set. And likewise associative law, alpha multiplying x plus y should equal alpha multiplying x plus alpha multiplying y, that is vector addition. Okay. Similarly, alpha beta, if you have 2 scalars multiplied with x will be alpha x plus beta times x. These all look simple, but just imagine that you want to define a vector space yourself satisfying these 10 properties, right. You will find it that you can think of with some effort some ways of defining vector spaces, most likely they would have been already defined by somebody else. Finding a new vector space that satisfies 10 properties is not easy. Okay. So, there is a multiplicative identity like we had additive identity, now multiplier identity. If you multiply scalar get back the same like a 1 being there. Okay. All these are 10 properties that a vector space must satisfy. Okay. And we talked about this scalar field k, that k has satisfied 4 properties which are listed here. That is, if there are 2 numbers a b, a plus b should be equal to a, like commutative nature. And a plus b associative plus c is same as a plus b plus c, and then there should be additive identity, a plus 0 should give rise to a or 0 plus a should give rise to a, that such as 0 exists in the scalar field. Additive inverse, there is a corresponding minus a, so that sum of them will be equal to 0. These are scalar field properties. So, when you have scalar field satisfying these 4 properties and a vector addition and scalar multiplication between a scalar field element and vector space element and these 10 properties we discussed now satisfied, then you have a vector space. Okay. And there are few more actually, this is not the 4 here for scalar multiplication, that they correspond to the vector space 10 rules, a dot b with scalar multiplying, b dot a and the rest. Okay. There is a multiplicative inverse, a inverse and like a reciprocal, our usual arithmetic notion, all that will be there. Okay. So, this is what is called the vector space. This vector space we need to make so much of the discussion here, insert new page. Okay. So, why do we need to worry about these vector spaces so much? Because our function space, okay, is actually a vector space. Our function space is a vector space, meaning that associated function space there will be a scalar field, there will be vector addition defined, there is a scalar multiplication defined, meaning that this function space that we consider satisfy the rules of vector space that we just discussed. Why do we need to discuss so much? Okay. Let us take a simple example from mechanics to understand why do you need to worry about this function space. It is just a group of functions, we can just leave it at that, but actually it is not as easy as that, because if I take let us say a problem where I take a string that is taut, okay, that is pulled with some tension. So, it is a taut string. Okay. Now, when I apply some force on it, let us apply a force. What happens? It will deform. How does it deform? It is going to deform something like this. Okay. Now, you ask the question, when we think about this minimum potential energy principle, any elastic system, or for that matter any system, tries to achieve minimum energy, minimum potential energy to reach its static stable equilibrium position, right. Similarly, this string also, when you apply the force, it wants to go to a configuration where it will have least potential energy. So, it takes this form. It also has, if you think of this as a optimization problem for minimizing potential energy, that is also a functional, as we will see later, or already we have seen when we discussed the geometry and mechanics in calculus of variations. There are a lot of possibilities, but it takes this particular shape, right. But you can see this particular shape has a kink in it. So, we are not saying all differentiable functions are the ones that we have a function space here, right. For this, there are a lot of shapes here. They can be shapes like that, there are shapes like this, the string can take, right. So, now what do we make of this function space? What should be there? So, only continuous ones, but then even discontinuous things are possible. So, let us just take an example. If I take and get something like this here, which is really discontinuous over there. How do I do that? I have to take a wedge of a form like this. Okay, imagine that I have a wooden block like this from that side, and then another wooden block of matching profile. I squeeze the wire between these two. So, this green line that you have shown has no option than having this discontinuity. So, I need to allow those also here, discontinuous functions. Okay, they are there and then sudden discontinuity and then go there, because the string needs that also. So, we need to define what this function space is, which we will continue in the next lecture.